Alright, in today's video, I'm gonna show you how to read math as a software engineer. So I received this question on Reddit and I thought it was a really great question. One that I've had to ask myself a couple times until I got the hang of it. So the question is, with mathematics, like when I'm trying to read a journal paper, I don't have the fundamental understanding to try to decipher the algorithm or what they are trying to explain. It's like a different language to me. What are some ways to go about deciphering these kind of situations? So the user is a senior developer and he's having trouble with math. You don't need to know that much math to be good at let's say web development or some field in computer science, but knowing math and being able to read it sure is a hedge. So to answer this question, I've got help from a colleague to answer that one. So one of my lab member showed me a system he used to get comfortable with the math. The guy was really proficient. He was able to read like formula like it was nothing. So he could read a paper and explain to me what the formula were doing in high level detail. I've always thought that he was just like good at it, but when he showed it to me, it's actually reachable for anyone to be able to do that. So I've used this technique for about 3 years now, and it's great, and I'm able to read pretty much anything, no matter what the complexity is. So it goes like this. So the first step is to read the paper, the math segment, whatever, fully. So you read it from the beginning to the end, and while you're reading it, take note about what you understand and not. Like he said, this was to put a boundary on the knowledge that is required to understand this paper. You cannot know everything, right? So it's a way of anchoring yourself and knowing where you have like some more blurry zone. So the first pass is really important, but you should not stop there, right? At this point, there's always a formula or two or all of them that you don't get. So at this point, you have a good idea about the paper. So the next step is to pinpoint structurally where you're a bit fuzzy. So what does that mean is that, okay, the introduction I got it, the conclusion I got it, the method, there's this part I don't get, the part about whatever I got it too. So at the end, you're left with like some blobs of section where you're a bit fuzzy. So then this is where it gets interesting. You take the topmost formula, so the one with the 1 on it, and the topmost formula that you don't understand, and you write it on a sheet of paper. So you take it out of the paper or the segment that you're reading, and you do the following. So you take your time to decipher that formula in isolation. So you do this. You find what each of the variable means. Right? This is super important. You cannot just read it. Most formula you cannot just read it from left to right easily. You have to like really understand what each of the symbols mean, and you have to say it in your head. You're like, this is momentum, this is epsilon, right? Not just like E, J, blah blah blah, right? You find what each of the indices mean, and then you chunk the formula into sector. So at this point, you know what the variable are, you know what the operation are, and you're gonna chunk them, and you say, okay, this is the numerator, this is the denominator, there's also this other section that is the root mean square, whatever. You chunk all of these, right? And then you repeat for all formula, and then you go slowly like this, right? And you make sure that you understand every bit and every segment before you move to the next formula. So this way, you're gonna take, let's say, 30 minutes on the first formula, it's fine, but now you understand it, and now it's not fuzzy anymore, and you can even write it in English next to it. So this is a system. So let's go to an example to illustrate my point. I'll go through a formula I haven't checked before. I'm familiar with stochastic gradient optimization. I've done some from scratch video on it. But here I'm gonna use something that I haven't read the formula yet, just so that you see me struggle a bit. Alright, so here we are, we're on Wikipedia right now. So this is stochastic gradient descent section. I've read pretty much all of this, so I understand all of them. I went through all of these formula, and now if you look at the end, we have this one, right? I haven't read it yet. I know roughly what Adam is doing, so it's the same thing as all of these stochastic gradient descent optimization. However, I don't know, and I haven't read this paragraph. So let's say I'm reading it. So okay, I get it. It's the same thing as RMS prop, right? And a delta. It makes sense. I know a bit what those two are doing. It's using the running average of gradient and the second moments of the gradient. So I think the second moments mean it's another derivative. This I'm not sure. So second moments. Okay, so second moments plus running average. So it has to do with those. Running average, I'm familiar with it because RMS prop is using the same thing, and this is like a pretty simple setup for a running average. If you see that thing, you know it's a running average. I know that. This I'm not sure. Given parameter WT, okay, so this is the theta, this is the parameter, and the loss function blah, where t is the index of the current training iteration. Perfect. Adam's parameter is updated. Update is given by this. Okay, good. And then, so this is the formula. I'm not gonna read it. Okay, here, well, actually, I'm gonna read it. So this is the this is I think the moment. It must be the moment. This, I don't know what VW is, but this look like a running. No, it's not a running average. Well, yes, this is a running average, and this is also a running average. I don't know what beta is though. Yeah, I'm not sure about these, but those look like running average. So yeah, so those are running average. I think that's pretty much what the difference between those two is. That this is the same thing. This is a gradient like this one, right? We have gradient over here, but this is exponent 2 and this one is not. And we have b1 b1, b2 b2, and this used the decay factor. So I think those are decay factor. So I think beta are decay factors, and this is saying that we can set different decay factor for both of them. And the only difference between the two is, well, the two difference between the two is the decay factor and the exponent 2. So over here, I think this is what they meant by second moment. I have to Google that afterward. Perfect. After that we have this m hat, which is that thing, divided by 1 minus b1, and this, so those are normalized stuff, I guess. So you do this transformation over here, and then those are the weight. This is the parameter, so those are the theta, and then the new theta is equal to this theta minus the learning rate. I think this is a learning rate because this is what they've been used as a learning rate everywhere, times this divided by the roots, the root square of the square root, sorry, of this plus epsilon. Epsilon here, I know why it's there. They didn't put it here, but it should be there. It's to avoid the division by 0, so it's a really small number. Good. Okay, perfect. So this I got it. This setup I've seen a lot of time. It's how you normalize the learning rate so that it's not that important. But I don't know why it's here. It should be I think it should be up on top over here, because anyway it's n times this, so you could put it there. In my head I will put it there, just so I get the setup a bit better. Okay, b1 and b2 are given to us. So the forgetting factor, so now it's not a decay factor anymore, they call it a forgetting factor. Okay, so that makes sense. For gradient and second moment of gradient. So I think, what is a moment? Moment in math. Specific shape of a function. Okay, so what is the second moment? What the fuck? Well, that looked like a square root. I'm not too sure about that part. So here they're talking about the variance, but I don't think that applies. I don't think that's the variance. Is it? Because that's a gradient. Just gonna go up for the Q. Here. Okay, so this is the Q, and it's more or less function. That's a Laplace function. Trying to minimize this, so okay, right. I don't know. What do they mean by that? Okay, we might be better off looking at for different parameters, estimate the first and second moment of the gradient and blah blah blah. Well, that's it. It's the gradient and then the gradient square. And this, okay, I think I get it. This is supposed to be a mean. I don't get it. I don't get that. Okay, right. So here they get the gradient with the stochastic time step. And then over here, it's the same formula as before, just written a bit differently. Here you get that, right? But because it's stochastic gradient descent, you only take one sample. If you were to do gradient descent, you will take like the whole thing and you take the average. So that will give you this. And I think this is what they're meaning by the second moment being the variance. I think this is it. Like the second, if you look, it's the variance. How is the variance defined? Yeah, the variance is defined. So you have the expectation of x minus that. So it's the expectation minus this to the 2. So that might be the variance. It's the expected value of the square deviation from the mean. So x minus mean exponent 2. So I think that makes sense that they're calling it that second raw moment. And it's an estimate. So I think that can be thought about as the variance, but it's really like this. In this particular case, it's the gradient on one point, on one sample, right? This is the first moment. Exponent 2, that's the second raw moment that they call it. And then here, they're bias corrected for the first and the second one. I think they need to do that. So bias. Why are they doing a bias correction? The good news that, well, however, it is moving average ensures the vector leading no instrument is towards 0. The good news that the initial range can be easily contracted, resulting in the bias corrected estimate, blah blah blah. Okay, good. So they are doing it to be not biased towards 0. This is great. So this is as much as I need to know right now for the Adam thing. To understand this thing, I just need to understand that this is the second raw moment, so it's not really the moment as defined as the variance. This is the first moment, but not as defined as the mean, because this is actually like, because it's stochastic gradient in a sense, it's just like one stochastically selected point, so it's an estimate of that mean. Because it's stochastic gradient descent. So those two understand because it's running running average of an estimate, a raw estimate of the first moment and a raw estimate of the second moment. So this is I got. These part, we're taking those estimates and we're de-biasing them towards 0 because we initialize that stuff, those two, at 0. And then we put those things here. And we need to take the square root over here because there's an exponent 2 over here. And this is the same story as this one, the RMS prop and add a delta. This I know, so I can think about this, and we know we have to put it the square root over here. So this is great, and the plus epsilon, I know what this is about. And if you look over here, the learning rate is over there, and we instead of putting it here like alone like RMS prop, we put it times the running average for the first moment. That's it. And if you look, there is no gradient over here compared to this one where there's a gradient that we put there even though it's here. So in some respect, if I look at this and I look at RMS prop, which I know, it's as if this is like this one, but with a running average, while this we just put the gradient here. We take the difference over here, the gradient, we put it here on a running average. So it's almost the same thing as this, but without the running average being applied to the gradient. So if I had to rewrite this on my own, I would put the n over here and I put this over there to look like this, and I will make a note that this is like that. And that's it. And those I just need to replace. It's constant. So the B1 is this. I don't have to worry about it. Why it's 0.9? I know it's because they tried a bunch of stuff and then found that this initialization of the parameter are really good for deep learning purposes. So I know this is okay. I don't have to worry about it, and beta 2 is okay. I don't have to worry about it. And that's it. I've understood this properly, and you saw like it require a bit of digging and to fiddling around with it. But now if I read this, right, if I re-look at it, it all makes sense for me, right? Now everything makes sense. I know that those two parts are running average. I know this is to de-bias the thing, and this is the actual update. This part over here, this is the update. You can think of it of this chunk as a plus, and we're going to change this by doing the plus of the new change that we need to do. Perfect. The only thing that I'm missing is the learning rate. The whole purpose of the Adam and Aramis prop is to like not think about the learning rate, but from what I know, we can set it to like something like 0.1. I think is good enough. But now I know what every of the parameters are. So that's what I wanted to show you, a bit of the messiness when you read math. You shouldn't be stressed if you're googling stuff, if you're opening a research paper, if you're looking at the definition of everything. That's the point. But at some point, if this is what you're doing all day and you're always reading math, at some point it becomes natural for you and you're good at it. But it's a skills. It's not just like you cannot just read this and like keep everything in mind. You have to understand what each of the things are, and it also depends on the notation that the author decide to use. Sometimes they will use a notation that is completely different, so you have to not get discouraged, and it helps a lot to take notes and then to rewrite the stuff next to you. So that's it. I hope this was useful for you. If you have comments, a question, let me know. I'm always available to help, and have a great week.